Hey everyone, in the Chemistry 1111 Galaxy, it's Dr. Carroll here. We're talking about Chapter 6, Lecture 2, all about covalent Lewis diagrams today. We're going to be seeing more dots than on those ice creams you can get in the States, which are called Dots Factory. Okay, and I do things in a bit more of a holistic approach than the book does. The book goes really extra things that I don't think all of them is needed, but it's all okay. So we are in page 262 in the textbook, and we'll also look at some slides, and we'll look at some fresh paint. So we build Lewis structures according to a 6-step procedure. Count the valence electrons, assemble the bonding framework, I also call it a skeleton, placing 2 electrons per bond, place 3 non-bonding pairs on each outer atom, assign the remaining electrons to inner atoms, optimize to satisfy the octet rule, and then look for equivalent or near equivalent Lewis structures. There's also something called formal charges, which is going to help us decide what our best Lewis diagrams can be. So, we have to count all the valence electrons. And if I have an example of PCl3, let's just do that whole thing together. So PCl3, so phosphorus trichloride. Phosphorus is going to be the central atom because halogens like to be terminal. So I'll make a single bond because you have to have a single bond at least. And in fact, with halogens, if they're ligands, they will be single bonds in almost all cases. So phosphorus has 5 valence, chlorine has 7. There's 3 of them, so we have to distribute 26 valence electrons into PCl3. So I got 6, so I have to put a remaining 20, 2, 4, 6, 8, 10, 12, 14, 16, 18. And then the 20th electron, well, that's got to go on the phosphorus so that the octet rule is satisfied. Chlorine isn't going to get more than 8 electrons around it when it's in a ligand position. So this is not the geometry, this is just a valid Lewis diagram for phosphorus trichloride. We say that phosphorus has 3 bond pairs, BP for bond pair, not British Petroleum, but bond pair, and 1 lone pair, LP for lone pair. Bond pairs are also called bonded pairs or shared pairs. Lone pairs are also called unshared pairs or non-bonded pairs. But bond pair and lone pair are the easiest one. And each chlorine has got 1 bond pair and 3 lone pairs. So that is the Lewis diagram for PCl3. Okay. So now let's try BF4-, example 6,3. So that is an anion. So boron gives you 3. Each fluorine gives you 7. Now it's an anion, so 1 more, so 32 valence electrons. Very rarely will you find the total valence electrons being an odd number. There's some weird times when that happens, but in our course, it's almost always an even number. So BF4-, so I'm going to put boron in the center because halogens like to be at the end. Fluorine is also more electronegative than boron. And the Lewis diagram, I'm going to put a square bracket and a minus sign there. I'm going to make them all single bonds first. Then I'm going to satisfy the octet rule for the ligands. So 6, 12, 18, 24, 26, 28, 30, 32. I like to count the lone pairs and then the bond pairs. You count it any way you want, but just make sure to check your work and get the correct number. You can't have less electrons or more electrons than what you're supposed to have. So this is a valid Lewis diagram for BF4-. They ask for 1 H3O+. H3O+, you remember it's called the hydronium ion. Oxygen likes to be in the center, so we're going to put hydrogens around the oxygen and the whole thing with a plus, and I'll put dots there. So oxygen is 6, each hydrogen is 1, so we have a total of 3, and then you subtract 1, so minus 1, so you got 8. 8 valence electrons. It's a cation, so you have 1 less electron. So I got 2, 4, 6, 8. There's my hydronium ion. There's a valid Lewis diagram. Okay, now sometimes we have parentheses with Lewis diagrams. And that's what we have in this case here, diethylamine. So you have two ethyl groups and then an NH. So we're going to have NH in the middle, and then we're going to have each of these CH2, CH3 groups is going to be bonded to the nitrogen. And because we've done organic chemistry before, you've done it way back in grade 11, you know that those are single bonds, those are ethyl groups, alkyl groups with two carbons, ethyl groups, and I still got 2 electrons left, and I put them on the nitrogen. And I'll let you count through, and you'll see that that is going to be valid. And so there you have it. Now it said build the structure for 2-methyl-2-propanol. Okay, so propanol, so I'm going to have carbon, oxygen, oh, ran out of room, let's go up here, carbon, oxygen, hydrogen, and then I'm going to have a carbon here and here. I'm going to have 1, 2, 3, 1, 2, 3, and so I'm going to have another CH3 group that I need, don't I? I missed that one. So I got C, that's a C there, CH3, there we go. So, you know what? No, what I did there is I did 2-methyl-2-propanol. No, actually, that's right. Let's count how many carbons. 4 carbons. Now that we have some questions here. 4 carbons. Yeah, I got 4 carbons. How many hydrogens? 10. 3, 6, 9, 10. Good. How many oxygens? 1. So there's my Lewis diagram for that. Now we talk about provisional structures. They make the molecule the most stable, and we sometimes have to do a bit more detail. So far it's okay. But let's go to here, formaldehyde. Now formaldehyde is an interesting one because you might think it's an oxy acid. It's not. So I'm going to have here the hydrogen is directly bonded to the carbon, not to the oxygen. So I have a total, each hydrogen gives me 1, so that's 2. Carbon gives me 4, oxygen gives me 6. So 12 valence electrons. So the book starts by making a single bond and then going from there. But I just go, what works? What works? What works is a double bond. I mean, you can start as a single bond, 2, 4, 6, 8, 10, 12, but carbon's not happy. So you have to make carbon happy by taking a lone pair and making it into a bond between the carbon and oxygen, and then the carbon is happy. It's got 8 electrons around it. The oxygen is happy with 8 electrons around it. So those are both examples for formaldehyde. Okay? And so there you have it. Determine the Lewis structure of ethylene. Ethylene is also called ethene. That's the UPAC name for it. The olden days was ethylene. So we'll have carbon, carbon, hydrogen, 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 hydrogen. So that is C2H4 is the molecular formula. The condensed, we got CH2, CH2. And so it has to be a double bond. A single bond won't work. You don't have enough electrons to make it a single bond. Okay? Now you can have, I mean, today we're just doing Lewis diagram after Lewis diagram after Lewis diagram, and based on how the online assignments work, you may get somewhere you'll use a drawing program which will help you to determine the Lewis diagrams using a molecular drawing program. Those are becoming more and more common. Acrylonitrile, I did a project once on acrylonitrile, or paper, in 1923. Acrylonitrile is used to manufacture polymers for synthetic fibers. Draw the Lewis structure of acrylonitrile. So it looks like I'm going to have a carbon and a hydrogen and a hydrogen, and then another carbon with a hydrogen bonded to that, and then a carbon bonded to a nitrogen. And if I count, I'm going to have I don't want to do it that way. You can do it that way. The molecule has 20 valence electrons. Does it really? 4, 8, 12, 17, 12, 15. 15 is 20, right? And then you just got to satisfy the octet rule. So you play with ideas here, And a carbon-nitrogen triple bond is a common thing that we'll find. And then we're going to have a double bond here. So you can have double bonds and triple bonds within the same molecule. Putting the double bond in other places won't fit right and won't make for a proper answer. So the final Lewis structure has the octet rule all satisfied for everything. You have C triple bond N with a pair of electrons on the nitrogen, and then you have the double bond there, so you have 8 electrons around this carbon, 8 electrons around this carbon, 8 electrons around this carbon, etc. Acrolein is used to manufacture polymers for plastics. Draw the Lewis structure for acrolein. So we're going to have CH2, and then we're going to have CH, and then we're going to have CH, I think double bond O. Is that going to work? There may be another double bond. Acrylonitrile acrolein, I think there might be a double bond here. Will that fit? Will we have everything fitting fine? Let's count how many valence electrons there are carbon. So 4, 8, 12, hydrogen, 1, 2, 4, so 16, and oxygen is 6, so 22, 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh, see, I haven't finished. I got to put the 2 lone pairs of electrons, 4 lone pair electrons, or 2 lone pairs of electrons, right? Be careful about that, onto acrolein. Okay, we'll get to resonance structures soon, but you can get more than 8 electrons, so beyond the octet in a Lewis diagram, but that only happens in nonmetals in periods 3, 4, 5, 6, 7. Not in periods 1 or 2, just in periods 3 and onwards. So 3, 4, 5, 6, 7. There's rationalizations. The atoms are bigger. There's more way electrons can get split out. The d electrons mix in. Various rationalizations. Bottom line is, for Lewis diagrams, which do have their limitations, as we'll see as we get to the next chapter, there are cases where you can have more than 8 electrons around them. So let's see an example of that. So in example 6.7 on page 267, and that's going to be to determine the Lewis structure of ClF3. So I have chlorine. Chlorine's more electronegative, so it goes at the end there. So chlorine is 7, each fluorine is 7, so that's 28. So I have to put 28. Well, the ligands have to be happy, and they're going to be single bonds, because halogens usually form single bonds. So 6, 12, 18, 20, 22, 24. Now I have to put in 28. So the only place they can go is around the chlorines. So the chlorine, the central atom, has 3 bond pairs and 2 lone pairs, and has actually 10 electrons around it. So is it a violation of the octet rule? I guess, but it's really just what Lewis diagrams say is allowed for chlorine, bromine, iodine, astatine, if they're in the center, tennessine, I guess. Okay, won't see much tennessine chemistry for a while, I think. So that would be the example, and that works. Let's try this practice exercise 6.7. Determine the Lewis structure of sulfur tetrafluoride. Okay, so sulfur tetrafluoride, S, F, 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 and F. So we got 4 of those. Sulfur is in group 6, so 6 plus 4 times 7, 28, 34 valence electrons. So I'm going to have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So 26, 28, 30, 32. And I got one more lone pair of electrons, and I'll put them on the sulfur. And there we go. Okay. Now there's another concept that will help us with all this, which is called formal charges. And this is something you probably haven't done before. Formal charge is the valence electrons in the free atom minus the valence electrons assigned to the atom of the Lewis structure. I do not like that definition for formal charges, so I'm going to give it a different one, which I think is better, from another book. Formal charge, or UFC, UFC, formal charge is the group number using the old system, so 1 through 8, minus a half the number of bonding electrons plus the number of lone pair electrons. So the formal charge is group number minus half the number of bonding electrons, not bonding electron pairs, but bonding electrons, and add that to the number of lone pair electrons, and you get the formal charge. And you calculate the formal charge for each atom, ligands and inner atoms, all of them. And the formal charge, it's a fictitious concept, but it does help us get stronger contributors to the Lewis diagram, because you can get more than one Lewis diagram. So the dream is to get Lewis diagrams where the formal charges are minimized, so each formal charge is as close to 0 as possible. If they're all zeros, well, then you've done the best you possibly can. So let's see, example 6, 7, which one was that? Chlorine tetrafluoride. So when I had ClF3, I'll rewrite it here. Okay, put the lone pairs on the fluorine, and then I had some lone pairs on the chlorine. So the formal charge on the chlorine is 7 minus a half of the number of bonding electrons. There were 6 bonding electrons and 4 lone pairs. So 7 minus 3 plus 4. So 7 minus 7 is 0. Okay, so my way of writing it is better than the way they wrote it, but their way of calculating it gives you the same answer. So just do it my way. I think it makes more sense. It's more clear. Now for the fluorine, that's going to be, each fluorine is going to be 7, that's group number, minus a half of 2, so that's 1 plus 6. So that's also 0, so this has to be the best answer. If I tried to make them double bonds between the chlorine and fluorine, my formal charges wouldn't all be zeros. For a neutral molecule, the sum of the formal charges must be 0. For a cation or anion, the sum of the formal charges equals the charge on the anion. Okay, so that's something to check, and always check, when you're adding up all the formal charges and all the atoms in your creature, that they add up to the total. Generally, the best Lewis structure is the one that results in minimum formal charges. Okay, if you have a positive formal charge on an inner atom beyond the second row, you want to try to minimize it. Okay, getting formal charges of 3 or negative 3, if you're getting stuff like that, you've got to look more closely, because those are very rare to find. Even formal charges of 2 and negative 2 are not that common. I mean, they're there, but they aren't that common. They don't coincide with the best possible Lewis diagrams, best way to describe the bonding. And sometimes Lewis diagrams totally fail, and you can't use them, and you got to talk about molecular orbital theory, MO theory. So let's try example 6.8, sulfur dioxide, using this idea of formal charges. And I'm just going to write it on a piece of paper here, so I know formal charges, because I'm flipping the pages on me, so I'm just going to write it down again. Fc on each atom is the group number minus, then in brackets, half the number of bonding electrons plus the number of lone pair electrons. Now I got it written on this little index card, and I can use it to go through the rest of them. So here we go, sulfur dioxide. And so we're going to look at some possibilities for sulfur dioxide. And so one of them, I'm going to have 18, right? So I can have, here's one way to get 18. 2, 4, 6, 8, 10, 12, 14, 16, and then put a lone pair on this sulfur in the middle, and this turns out to be the best representation, even though we have more than 8 electrons around it. Some books call it expanded octet, but an expanded octet is still an octet. Expanded valence is a better way to say that, not expanded octet. So SO2, so let's see, the sulfur, the formal charge for the sulfur would be 6 minus a half of 8, right? 1, 2, 3, 4 times 2 is 8, so half of 8 plus 2. So that's 6 minus 6, so that's 0, so that's good. So the formal charge on the sulfur is 0, and on this oxygen is going to be the same as that oxygen. So it's going to be 6 minus a half of 4, so that's 2 plus 4. So 6 minus 6, so that's 0. So you have a formal charge of 0 on all of them. Okay? So that is the dream. What are some other possibilities? I could have this, where I have one's a double bond and one's a single bond. Okay, now is that going to give me 18, 2, 4, 6, 8, 10, 12, 14, 16, 18? Yes, it does. And I could just as easily have it the other way. Have a single bond here and a double bond. But already some of you are saying, why would one be a double bond and one be a single one? They're both oxygen and there's a sulfur in the middle. So let's look at the formal charges. Here I would have 6 minus 1 plus 6, 6 minus 7. So the formal charge here would be negative 1. Sulfur here would be 6 minus half of 6. Sometimes you just count to 6. So 6 minus 3 minus 2. So that's plus 1. And then this guy's 0. So yes, they add up to 0, but they aren't minimum, right? Minimum, I mean getting as close to 0 as possible. Okay, the way you get to it isn't the big deal. It's like how close to 0 can you get? So you've got minus 1, 1, and 0. If I write the other way here, I'm going to have 0, 1, and minus 1. So the representation of one as a double bond and one as a single bond is not as good as Lewis diagram where you have 10 electrons around the sulfur. So the representation here is our best one. Where do we have one where the formal charge of the sulfur is 2? I didn't see anyone where the formal charge is 2. Well, there you don't even finish the electron. Okay, so anyways, I got the final ones and then I assigned the formal charges. Okay. Determine the Lewis structure of phosphoric acid. Know that each of the hydrogen atoms are bound to an oxygen atom. Okay, this is a good one. So first of all, you'd think, and I think we looked at this already before, didn't we? We have phosphorus in the center, then we have oxygens around, and then we have hydrogens bonded to the oxygen, and then a lone pair bonded to the phosphorus. So this is one way to draw it. Let's finish it off here. Okay, so the formal charges on hydrogens are going to be 0, right? It's going to be group number 1 minus a half of 2, and there's no lone pair. So the formal charges on hydrogens are 0, so usually don't even bother to write those in. For the oxygens, let's change the color here. The ones where there's single bonds, those are all going to be 0, right? Because it's going to be 6 minus 2 minus 4, so 0, 0, 0. So it all comes to the phosphorus here. The phosphorus is going to be 5 minus 3, which is 2 minus 2, so that's 0. Okay, so this one is the best one. I'm thinking of something else. So that's good, and I don't think there's a reason to try. Should I try to do a double bond? Not have a lone pair? Okay, I guess I can try that. So let's try a double bond to one of the oxygen, and then a hydrogen, and then an oxygen, and an oxygen. H3P. Now, there is something here that I just realized. I got H3PO3, right? That's not what the phosphoric acid is. It's H3PO4. So I was wondering, why is this question appearing here? So I'm going to go to the to my canvas here, my paint, and I'm going to do a new drawing here. So H3PO4. Okay, I thought there was something a bit odd there. So here's H3PO4. So I'm going to have phosphorus. I'm going to have oxygen all the way around it. And then I'm going to have hydrogens bonded to the oxygen. 3 of them. And let's make these all single bonds. And let's make this a double bond. And let's figure out this here on the oxygens. So hydrogens are still 0. The oxygens that are singly bonded to the phosphorus are going to be 0. The oxygen at the top is going to be 6 minus 2, 4. 6 minus 2, so that's 0. And the phosphorus here is going to be 5, group 5 minus 5, so that's 0. So here they're all 0. I made a double bond, so I have 10 electrons around the phosphorus. So that's okay. That's good. So you're going to say, well, I don't like that. You got 10 electrons around it. Can you draw it instead like this? We have just 8 around it. Well, how could I have just 8 around it? Okay, H3PO4. Oh, I guess I could have like just all here. Let's double check that. Where I have 6 electrons around a singly bonded oxygen without bonding to the hydrogen. Do the number of electrons work? There's going to be 5 plus 3, 8 plus 24, 32. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, 32. 6, 8, 10, 12, 14, 16, 18. That's all the lone pairs. 20, 22, 24, 26, 28, 30, 30. Yeah, this is 32 as well, and the octet rule satisfies. So you're going to say, oh, this should be the winner, the one on the right. Well, guess what? It's not. Because if you look at the formal charges, the one on the top, the oxygen on the top is minus 1. 6 minus 1 is 5, minus another 6. And the phosphorus in the center here would be 5 minus 4, which would be plus 1. Okay? So you have formal charge set where one of the phosphoruses is plus 1, one of the oxygen is minus 1. Yes, the whole thing adds up to 0, but the one on the left has everything at 0. So by expanding the octet, by having 10 electrons around the phosphorus, we have a better choice, a better representation of the molecule. Because really, this oxygen at the top is not the same as these other 3 oxygens. Once these 3 oxygens are bonded to a hydrogen, then they are not equivalent to the oxygen at the top. Okay? So I'm glad we did that one. Let's go back and see. So that's phosphoric acid. Now we're going to try one vinegar, acetic acid. We see that one a lot. Here's the Lewis diagram. And so the only thing with vinegar, the only 2 things we can really change, I'm going to write the second possibility here. Okay, I can have a double bond to this oxygen and a single bond here. So the carbon's happy. This carbon here has got group number 4, minus 4, so it's 0. That's nice. This oxygen is going to be 6 minus 2 is 4 minus 4, so that's 0, so that's nice. This oxygen is going to be 6 minus 2 minus 4, so that's nice. So everything's nice there. So that is an example for a good minimized formal charge for acetic acid. The other way to do it would be to have a double bond to the oxygen which is bonded to the hydrogen, so then there can only be one electron. Only a single bond between the carbon and the oxygen at the top here, which would mean the oxygen still has a formal charge of 0, so that's good. But the oxygen at the top will be -1. The oxygen bonded to the hydrogen, so known as the acidic hydrogen, would be 6 minus 3 minus 2 would be +1. Okay, when you're getting oxygens with pluses, that's not really a good way to draw a Lewis diagram. Yes, the formal charges add up to 0, but they are minimized. So your best description using Lewis model for acetic acid is the one I just put a box around. And then they go through the whole thing. Oh, they really get graphic with it, but this big slash through the one with the -1 and the +1. Carbonic acid, I'm going to let you try that one on your own, as well as the practice problem 6.25 and 6.26. Okay. Now, the final topic in Lewis diagrams, and this is something you probably haven't seen before, is it's got this unfortunate name, which actually comes from physics, resonance structures. And just don't worry about the history. It just means where you can have more than one contribution to a Lewis diagram, and your actual final description is a mix of the contributors, and it's called a resonance hybrid, right? Hybrid, you've heard that before. Hybrid cars, hybridization in plants. You take wheat and flax together and you get wax or fleet or whatever. You can get more than one equivalent structure or near equivalent, and nitrate's a good example of that, and it'll have 3 resonance structures. So what's the best one? Well, they're all identical, so you take an average. So here I have in the margin here, rather than completely reinventing the wheel, I can put a double bond at the top here. They didn't put the square brackets around the minus sign, but they should. Or I could put the double bond here, or I could put the double bond here. I'm not changing the skeleton. I'm just rearranging, shifting around where the electrons are, but I'm not changing the positions of the nuclei. And you see for the nitrate anion, where I got 5 plus 6 plus 6 plus 6 plus 1 more because it's an anion, 24 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, that I can have 3 possibilities. And the formal charges, well, let's see, on the nitrogen, it's going to be 5 minus 4. There's no lone pair, so it's +1. This oxygen is -1, -1. And this oxygen here is going to be 0, right? So I'm going to have formal charges. They aren't all 0, but they do all add up to be -1. And then if you just shuffle them around, you still have a 0, -1, -1, +1, 0. That's just a typo there, isn't it? Oh yeah, here, fix that up. 0, -1, -1, and +1. So those 3, sometimes you write these wide arrows here to show the resonance structure. So there's 3 equivalent resonance structures associated with nitrate, and you can write the resonance hybrid. The book doesn't always write it like this. I won't bother with writing the electrons on the side, but you just put these little dashes here, and you say the bond order is 1 1/3, and we'll get to bond orders a little later. Determine the Lewis structure for dihydrogen phosphate. So here's an example here, 610. So there's going to be 2 resonance structures associated with this one, and so this is an anion. So let's here's one dihydrogen phosphate. So it's like phosphoric acid, but I've taken away H3PO4. I've taken away one of the protons, so I got a minus charge here. So I can write it like this, and let's count, make sure 32 valence electrons. Really, what was the thing again? H2PO4 minus. H2PO4 minus. So 5 plus 2 is 7 plus 24, 25, 32. Yeah, 32 valence electrons. So I'm going to have 6, 12, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. What am I doing? I've created 4 more electrons. It has to be 32. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Good. Okay, so that is one possibility. And we see for this example that what's happening for this example here is that the formal charge on the hydrogens is 0, good, and on the oxygen we have 0 here, 0 here, oxygen at the bottom is -1, oxygen at the top is -1, and phosphorus is 5 minus 4 is +1. Okay, the question is, can we do better than that? And if we make one of the oxygens instead, oh, I should shut off my phone, right? Yeah, let's see, don't have your phone on when you're doing this. Okay, I can make a double bond here, so phosphorus, then oxygen, and then oxygen and hydrogen, and then oxygen and hydrogen, and then an oxygen at the top, and then we're going to have a minus sign here, and so we're going to have the hydrogens are good, the oxygens are good, the oxygen's -1 here, phosphorus is 0 now, and the oxygen at the bottom is 0. So if you make one of the phosphorus double bonded to an oxygen, you still have 32 electrons, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. You still have 32 valence electrons, but the formal charges are minimized. So both descriptions or contributions, or both contributions describe the bonding, but having the one on the right with formal charges more zeros in them, right, more minimal than the one on the left, means it's the majority contributor and the other one is a minority contributor. Okay, they both contribute, but one's a majority and one's a minority. Okay, and you can try the acetate anion on your own, and one of them will have formal charges less than the other, and that'll help you get the resonance structures for that. Now, resonance structures aren't always equivalent, and the optimal set includes those forms with the least amount of formal charges. Here's one which has 3 nearly equivalent resonance structures. Okay, and it is the propellant in whipped cream, dinitrogen oxide. The connection of the order NNO. So we want to get the possibilities for NNO, and 5, 10, 16 valence electrons. So we can have double bonds here, 2, 4, 6, 8, 10, 12, 14, 16. Nitrogen is -1 there, +1 and 0, right? It all adds up to 0. So this is one contributor to the Lewis description, one resonance contributor. Then I could make it an NN triple bond, and here I have an NO single bond. So 2, 4, 6, 8, 10, 12, 14, 16. So nitrogen on the left is 5 minus 3 minus 2 is 0. In the middle is +1, and at the end is -1. And then on the left I could have a nitrogen oxygen triple bond, and so I could have 5 minus 6. Now why does it say -2? Well, because there's a bond. So 5 minus 1 is 4, minus 6, -2. Then a plus 1, 5 minus 4, and then a plus 1 here. 6 minus 3 is 3, minus 2 is 1. So that does add up. They all add up to 0. But this one on the right, when you're getting things at -2, that's nasty. That is unreal. Not a good contributor. It'll be like, I don't know, 1% maybe in the description. The one in the middle looks the best. I mean, they both have 0, 1, minus 1. But all things being equal, you want the more electronegative atom to have the negative formal charge, and it does. The one on the left doesn't. So my best answer is a mix between the one in the middle and the one on the left. Third structure shows more accumulation than the first two. The optimal structure is a composite of the first two, but not the third. Okay, so the book really didn't go into more detail about it, but even though it's a mix of these two, it's a weighted mix. This one we're a bit happier with than this one. This one we're a little happy with, but not as happy as the other one. Okay, ozone. Ozone is happiest, and I looked at something like this before, where you're going to have, now again, oxygen doesn't usually like to violate the octet rule, does it? But you're going to have 18, so 2, 4, 6, 8, 10, 12, 14, 16, 18, and then you're going to have, let's see, 0, 0, and here you're going to have 0, so you're going to have zeros for all of them. If instead I make one a double bond and one a single bond, well, the single bond is going to put a ring on it. I'm going to have 0 here, plus 1, and minus 1. So that one's not as good. It's not as good a contributor. Let's see how they do that at the end of the book. I'm curious about that one. That was example 611, practice exercise. Not at the end of the book, sorry, at the end of the chapter. This chapter is different than the end of the book. So well, they show it just has do I have too many electrons here? 2, 4, 6, 8, 10, 12, 14, 16, 18. That's 18. That shows it. Now, this is controversial here because we said that the octet rule would only be allowed to be expanded if it was more than 2. So, if you're going to go by that, then your discussion where you're going to have a resonance hybrid between this one and the one on the right is more valid. So we won't use this. Now, if we talk about MO theory, there's actually some things where we can discuss where we would use it. If it's SO2, like we did earlier in the chapter, then definitely you put the lone pair on the sulfur, because sulfur's on just two of them. Sulfur's in the third row. There's 2 of them, and there's 2 pair. But with oxygen, there isn't. So Lewis diagram for ozone breaks down a bit. Now we'll talk more about, in fact, we're going to do ozone when we talk about molecular orbital theory. Okay? So then there's some practice ones for you to try. Determine Lewis structures for Br2, NCl3, BrF5. Some other ones, 6.22, and some ions, including possible resonance structures. Okay, so get some practice with that, because this Lewis structure really does need lots and lots of practice. And then we'll talk about molecular geometry next time. Have fun.